I'm Stefano. I'm actually in the computer science department. So I'm the kind of guy that likes to think about how to use machine learning, AI, data science techniques to come up with new ways to approach the kind of problems that Gretchen and Pascaline have been talking about in the previous talks. So as you've heard in Gretchen's talk at the beginning, our society is facing some pretty formidable challenges to sustainable development. There is close to 1 billion people around the world living in extreme poverty. We need to find ways to feed a growing population, find ways to deal with climate change, find new sources of affordable and clean energy, and so forth. So you can see here, these are the UN Sustainable Development Goals, kind of like the big priorities that the international community should be focusing on all the way to 2030. And so clearly these are very, very important problems. One of the challenges is that we actually know they're very, very hard to we have these goals, but they are very hard to measure. They're very, very hard to track. Turns out that we know very little, as Pascaline was saying, we know very little about what's going on, especially in the poorest part of the world. There's this big data divide between developed and developing countries. Here we are putting sensors everywhere. We're measuring all kinds of stuff. If you go into developing countries, we actually know very, very little about what is going on the ground. So there is this big problem that we have these very, very ambitious goals, but we don't know how to track them. We don't know whether we're making progress. We don't know whether policies that we're implementing are working or not. For social scientists like Pascaline, it's very, very hard to do research. It's very, very hard to figure out what are the environmental or economic or societal kind of like drivers of the variation that you see on the ground with respect to, say, poverty or food security or the kind of problems that we all care about. And so some of the research that we've been doing in my group is really to think about, is there a way in which we can use the latest developments in machine learning and in data science to track these targets, these goals that we all care about in a very inexpensive and scalable way, right? That I think is the big promise of machine learning and AI and computer science in general is really scalability. The idea is, can we take unconventional data sources that are cheap, they are passively collected, they are available on a global scale, they are updated frequently, things like satellite images, remote sensing data, social media data, phone records, those kind of things that basically are available all over the world. And they clearly contain some information about these kind of socioeconomic indicators that we would need in order to track progress toward these goals. But the challenge is, how do we actually extract useful sort of like bits of information from these data streams that are unstructured, they are massive, and they are difficult to deal with, right? And so one of the kind of like the research question for me is, how do we use the latest developments in machine learning and AI to actually extract actionable insights from all these unconventional data streams so that they can be used by tools like Invest to actually help decision makers to make better decisions and come up with better solutions to these problems. So what I will tell you is some of the work we've been doing on tracking poverty and food security issues, which are sort of like number 1 and number 2 on that list of the 2030 agenda. So with respect to poverty, as Pascaline was saying, the kind of data that we have is really, really bad. This is a map of the African continent showing the availability of survey data in those countries in the decade from 2000 to 2010. Countries that are colored white, that means that basically there is no survey data available for that country for an entire decade. You can see that most of the countries are pretty light, and that's kind of like an indication of the kind of the quality of the data that people need to work with when they think about development problems from an analytic perspective. Now, on the positive side, we are in the middle of a sensing revolution. We are getting access to increasingly good remotely sensed data, in particular things like satellite images. They are getting better and better. There are a number of private companies that are entering the market. They're driving the costs down. The quality of the sensors is improving. These days you can get access to pretty much every corner of the world of images with very, very high resolution, where you can see all kinds of things that we would imagine are sort of like related to various socioeconomic indicators that we might want to track. Like you can see a busy shipping yard where you can almost count the number of containers that are there. You can see the kind of infrastructure that is available in a certain area. You could almost count kind of like the vehicles and the cars that are there in that location. These days, you can even get access to high-resolution videos from space. These are actually available sort of like commercially right now. And again, I mean, you can imagine that with this kind of data, like there is really a lot that could be done if we combine this with sort of like the latest developments in machine learning and deep learning in particular. We're getting access to all this amazing imagery. Essentially for every corner of the world. These days you can get, there are companies that are basically getting images of every part of the world updated every day with say like 3-4 meter resolution. And you can imagine that combining that with the latest developments that we've seen in computer vision and deep learning, we can really imagine to build a system that can track sort of like the health and how the planet is changing with extremely high spatial and temporal resolution. As you probably heard, there's been a lot of progress in computer vision and machine learning thanks to the use of deep neural networks and deep learning tools. We've been able to do pretty well at the task of say classifying images, figuring out what's going on in an image, tracking objects that move in a video. These systems are reasonably good, they're pretty reliable, and we can start thinking about what happens if we combine them with all this new data that is becoming available and really try to build these systems that can track all kinds of things in a scalable way, right? In a scalable and inexpensive way. So one of the first projects that we tried was to see to what extent we can actually predict various kinds of poverty indicators from high-resolution satellite images. The challenge here is that when you think about development problems, the amount of labeled data that is available is actually pretty scarce. So you cannot just take your favorite ResNet, your favorite deep learning model and train it off the shelf. We just don't have enough labeled data to do that. So in order to get these things to work, we actually had to come up with some new techniques, combining some transfer learning and some semi-supervised learning. One key component is the idea of using nighttime light intensity that Pascaline mentioned before as a proxy for economic development. The idea is that we have very limited data about how rich or poor a particular location is because you actually have to send people on the ground. That's very expensive. It doesn't scale. But one thing that we know is how dark or bright a particular location is if you look at it at night. So what we can try to do is we can try to train our neural network to predict for any given area in the world whether or not that location is going to be bright or dark at night. So if you show the neural network something that looks like a forest, it should predict that it's probably going to be dark at night. If you show the neural network like a pretty developed city, it should predict that it's going to be pretty bright at night. And the advantage is that for this problem, we're in a regime where sort of like deep learning shines. We have essentially an infinite amount of training data. You can construct a massive training data set of images and the corresponding nighttime light intensity, and you can train your model to solve this task. And the hope is that by learning how to solve this task, the model will learn something about the kind of visual features that are predictive of economic development. Indeed, it turns out that that is the case. These are some of the filters that the model learns while solving this task. These are the kind of things that the model realizes that are actually useful for predicting whether or not an area is going to be bright or dark at night. You see that the model learn how to recognize roads, learn how to recognize buildings, bodies of water. My favorite one is the swimming pools. The model figured out that looking for swimming pools is actually a pretty good way of predicting whether or not an area is going to be dark or bright at night. And what's exciting here is that we never had to provide any label, like the model figured out by itself the concept essentially of a swimming pool, these kind of like semantically meaningful features, just by trying to predict the amount of nighttime light intensity. So we kind of like got around the labeling problem. We used this transfer learning idea, predicting night lights, to pre-train our model, figure out a lot of infrastructure things that then we can use to actually predict. Using the limited amount of training data that we have about poverty, we can try to fine-tune the model and see whether all these features that the model learned to identify to predict nighttime lights are actually useful for predicting poverty. Turns out that the model works quite well. You can say, if you apply it in Uganda, you try to pick villages for which we have measured ground truth using surveys. You try to predict how rich or poor that area is just looking at satellite images. You can get an R-square of about 0.7, so you can explain about 70% of the variation in the data just by looking at satellite images. So that's exciting because that means that we have a system now that we can use to produce very high resolution and very poverty maps for essentially any part of the world. Here are some examples in a couple of African countries. We did it for a few of them in the African continent. And as you've seen, this is not perfect, but it's actually pretty accurate. And it's exciting because we can keep these maps updated frequently. The only thing that you need are images, and you can just feed them into the model, millions of images, and you can produce these very high resolution poverty maps, and we can keep them updated very frequently. So yeah, we got a lot of interest on this, number of awards. Let me quickly move on to another topic that I think a lot about, food security. There's a growing population. We're going to need to find ways to feed it. We looked at whether we can use similar ideas, so combine unconventional data sources, which are like the latest developments in machine learning, to predict. In this case, we're looking at measures of infrastructure of agricultural productivity. So we wanted to see to what extent you can use images of the Earth taken from space and use them to predict how productive, let's say, a country or a county or maybe even a field is directly from space, basically by tracking how the vegetation grows from space. This is the system when we apply it in the US, where here we're trying to essentially, you see a map of, you see the Midwest, every little box corresponds to a county, and we're tracking in real time, making a prediction for how productive that county is going to be. Here we're looking at the production of soy, but we can do it for multiple other crops. The system is actually very accurate. Let me skip this, but sort of like we can do better than what the USDA does. The USDA actually has to go, call up farmers, collect samples in the fields. We can do slightly better just by looking at satellite images. So again, much more scalable. We can essentially apply it to any part of the world. We've extended this model to South America, India. We're now looking at Africa, and so we're pretty optimistic that we can finally get a pretty scalable way of tracking these kind of outcomes. We showed this to the World Bank. We actually won an award there. They were really excited about the opportunities that these kind of models present for tracking these kind of outcomes in a very scalable way. The other project that I wanted to briefly mention, but Pascaline already did, so I'll just go over it very quickly. You can also, we've also been looking at infrastructure quality, to what extent you can predict, whether or not people have access to electricity or water or sewage, these kind of things. And again, we got a pretty accurate model. We can get an area under the curve of about 0.85, which is not perfect, but it's pretty good. And again, it's only using satellite images, which means that we can now keep track of these outcomes in a very scalable and inexpensive way. We can build continent-wide maps and hopefully even move on from Africa to sort of like build a system that can track these kind of things on a global scale. And I think I'm probably out of time, but sort of like, yeah, that's the high level idea. The ambition is to combine the best advances in AI and machine learning with new unconventional data sources and build a system that can track all these kind of indicators that are very important to track the sustainable development goals in new ways that were not possible before. Yeah, thank you.